Welcome. So we're going to start chapter 4 by talking about proofs. We're only going to do a little bit of chapter 4 because we're going to transition into inductive proofs, and we're going to do a little bit of direct proofs. So I'm going to talk about what are definitions, why they're important, what are constructive proofs, how to disprove some universal statements with counterexamples, and then what is direct proofs. So first off, let's just talk about definitions. So if I asked you to define the terms even and odd, how would you do it? Now, a lot of people would probably say something along the lines that even, you might say even is a number that, uh, actually, let me rephrase it. Like some of the things I've seen, students define this as is even. That's a horrible even. I should really sorry. So I can still say that even is a number 0, 2, 4, 6, 8, and so forth. Well, the slight problem is this is a really long list. And good luck getting all the way through it. It's going to get infinitely long. You can't actually categorize on all of them. This is again going back to sets. When we tried doing the whole set roster notation, doesn't really work. So a different definition, someone might transition, say, okay, even is a number ends in 0, 2, 4, 6, or 8. So with this definition, that sounds like it would make sense because obviously we can go 248. Now we have to talk about what's it mean to ends in. We can take here and be like, okay, that ends, so this is even. That would be really good. The problem with that is what about the number 1.03948? It ends in the number 8. So therefore, this is even. However, that's not true because even means it's an integer, and this is not an integer right here. So all these definitions kind of end up getting muddled because we have to be very careful. What do we mean when we say a number? Do we mean an integer? Do we mean rational number? Do we mean so we have to kind of identify a little bit more information. We have to be very specific. In math, this is important. Let me give you a different example. It's not here on this paper, but just think about I'm going to erase this and kind of show you. What if I say two statements? I'm going to say the year starts in January. I will also say the year starts in July. Now, now obviously these are statements, they're either true or they're false. The truth is both could be true, both could be false. And the reason being, it depends on how you define the year. If we go by the calendar year, then obviously the first statement is true because the calendar year starts in January. However, if we're going on fiscal years, for instance, the university, its fiscal year actually starts in July. So they have to use up all their funds by the end of June and start the new for one fiscal year before they start the next. Some institutions, some businesses start their fiscal year at a different time. We could talk about when does the school year begin, and typically that's in August or September. So again, both these statements could be false. We're talking about school year. The key thing is then, what was the definition I had for the word year? We have a definition, and we have to be very, very careful because when we throw around words, we have to make the definitions clear. This is why notation is critical, because when we use notation, notation is translating what does something mean. And we have to be very clear or else there will be miscommunication. So this idea is really important. Now we're going to use even and odd in a bunch of our proofs. So this is going to play a role. But if we went further on even numbers, the technical definition is often this, because many people would say, I can divide it by 2. Well, what do you mean I can divide it by 2? Even that phrase, I can divide it by 2, doesn't make sense because, well, I can take 3, I can divide it by 2. What you really mean is divisible by 2. And again, the term divisible literally means that it is there's an integer. Again, notice if there is some integer k such that 2k equals n, then n is even. Further, we don't even just say it's odd if it's not even. The reason for that is because it's really hard to define something by what it's not. A much better way is to simply say it's odd if I can write it as 2 times some integer plus one more. So we are going to define, and we're actually going to use, these are the official definitions of even and odd because of the power they give, because they're very clear. There is no fuzziness. Often when you're learning things in elementary school, yeah, you probably were taught other things, but the problem with those definitions is they really actually weren't concrete and locked down, and they left ambiguity. And we don't like ambiguity. We want to be very clear. Another key definition we're going to talk about is prime. So when you think for a second, have you ever heard of a prime number? Well, prime numbers are any number n where n is bigger than 1. That's a key critical thing. 1 is not a prime number. So it has to be bigger than 1. So it has to be at least 2. It's an integer, so we're not talking about fractions, decimals, anything else like that. And if they're for any positive integer r and s, if n equals r times s, then one of those two are the r or s, one of them has to be n. Meaning, if I can write it as the product of two numbers, at least one of those numbers must be that number. And that means the other number has to be 1. So if r is n, then s has to be 1 and vice versa. On the other hand, by the way, there is something called composite, which is not a prime number. And it would mean that I can write this, again, I could do all the same, except I can say r and s are some numbers between, there exists an r and s where they're between, r and s are both between 1, bigger than 1, and smaller than n. So it can definitively kind of play with this. All right, so let's get into some key let's do some proofs and talk about. Constructive proofs are our first proof. Constructive proof are a way of building proofs, and they're really actually usually for there exists situations like this. So notice I want to prove that there exists an integer. Okay, wait. What does that mean just right there? Even before we read any more, there exists an even integer n. That means I just need one integer n that's even that satisfies these conditions. If I can find any one, then we're good. I don't even need to show this is always true because I only have to show it true one time. And it can be written in two ways as a sum of prime numbers. Well, let's just think about some even numbers that we have. And now the key part is two ways. So I can't really do 6. I can say 6 equals 3 plus 3. That's one way, but the only 6 is also equal to 5 plus 1. We might think this, but the problem here is 1 is not prime number. So we can't do that. And 3 plus 3, that's one way. We couldn't find a second way. All right, so let's take another even number. Let's go with 8. Well, I can do that one as 5 plus 3, but I'm stuck because, again, I can't find another combination. Let me give another one. I'm just kind of rattling through. And the nice part is, if we're trying to prove this by construction, we literally can kind of stumble our way through and test a bunch of situations. Constructive proofs, this works out for. And so I could say, well, I have 7 plus 3. Those are both prime numbers. Check, that's one way. But it's also equal to 5 plus 5, which are two other prime numbers. Boom, we just found two ways. Turns out, take 12. Well, 12, I can't really do 12 because if you try it a couple ways, you'll end up with, you'll get 7 plus 5, but there turns out there's no other way to do it. But if you go to 14, you have 11 plus 3 and 7 plus 7. So boom, we have another example. We can go up to the next, and there could be more than two ways to do it, but there has to be at least two ways for this to be satisfied. And we just found two examples, but all we need to do is one. So this is a constructive proof where you're simply showing it's true for one example. And it's kind of a proof by example. It's not, we really don't really call it proof by example, call it constructive proof. And it does have a small place. It's not a huge thing, but this is something that does come up from time to time. Now, we also like to disprove some statements, more commonly universal. So this one was an existential statement we're proving with construction. The interesting part is disproving universal statements with a counterexample is actually where those constructive proofs come in most often. Because to disprove, so I'm just come here, I'm going to come to a for all statement. Remember, what's the negation of a for all? It is there exists. So just real quickly, I'm going to write that down. So just a reminder. If it's not true that for all x, p of x, that is the equivalent, the same thing as saying there exists some x where not p of x. So wait, we just did a constructive for there exists. So if I want to show this is not true, all I need is one counter example, meaning one thing that breaks it. So let's look at this specific thing that I want to disprove. All I need to then find, so we need some AB, which are real numbers. So they're not be integers, such that A squared equals B squared and A does not equal B, because I'm trying to show this is not true, this is. So I want the if statement to be true, but the then statement to be false. Remember, that's the contradiction kind of situation we're talking about. So in this situation, can you think of any situations like this? I'm thinking of one. What if A is 1 and B equals -1? Well, 1 squared obviously is 1, which is also equal to -1 squared. So our A squared equals B squared. Check. However, 1 does not equal -1. If you don't believe me, go back to algebra. So A does not equal B. Check. I've satisfied my two conditions. We can talk about the fact that they're both real numbers, so we're good. And we have a counterexample that breaks our situation like this. All right. So those are all a bunch of our situations that we have to kind of work with and kind of understand so that we make sure we get this whole process done. What about something called a direct proof? Well, direct proof, it's kind of a proof by construction, but really it's more of just doing this. It's we're assuming, so I'm trying to show that if P, then Q. So let me just make a note of that. This is for proving something. So we want to prove this is often for P implies Q, or if P, then Q. So we start by assuming that P is true, and we want to show, based on that fact, that Q is then true. We have to somehow connect the dots from there. So this is a really, really important proof, and it's common. It's the most basic proof that we often talk about, besides just that really counterexample proof. So let me show you an example of that. Let's suppose that n is an odd integer. I want to show then that 3n plus 7 is an even integer. Well, the proof of this is going to be kind of, so what we're going to do is we're going to start with using suppose. Now I want to suppose this. This is what my suppose is. So I want to suppose that n is an odd integer. Well, by the definition of odd, n has to equal 2k plus 1 for some integer k. So I just use I just wrote down the definition, and now I'm going to say, let's consider. So now I'm going to let's consider 3n plus 7. Now, this is something I know some of you have been a little bit lackadaisical in your equal signs. You have to keep your equal signs really true. That if it's equal, they're equal. You don't use like an arrow, an equal sign if you mean an arrow. It has to be equal. But this, by substitution, is equal to 3 times 2k plus 1 plus 7. That is by substitution. Since n is this, I can substitute it in. I can substitute that in using that. By distributing, though, this is equal to 6k plus 3 plus 7, which notice is 6k plus 10, which is also equal to 2. I can pull a 2 out and I get 3k plus 5, but since 3k plus 5 is an integer, then we have an even number. So that means that 3n plus 7 is even by the definition, and we're actually done. And often a lot of proofs have a little square on the end or something else along those lines to kind of help. All right, play with those examples this week. That's what we're going to introduce. We're going to work from there.